Okay, so for PWM coding, let's close our old project. Close project. We have file new STM32 project. Okay, whenever you are creating a new project, you should keep your internet on. Okay, here we are going to put the name of the controller STM32 F103C8 P6. Let's select this one. Here we are going to name it as PWM. Finish. So here timers, we are having multiple timers. Let's consider timer 3. Okay, you can take any of the timers. Okay, here while selecting the channel, what you have to do? You have to select PWM generation CH1. Okay, so this is our CH1. Okay, it depends on the pin. For pin diagram, you can Google the pin diagram of blue pill. Okay, so here timer 3 is connected with A6. Okay, now you don't have to do anything over here. Now let's come to this point. So in theory session, I have told you that we are having CCR and ARR resistor. So this is auto reload resistor. So its value depends on the resolution of your controller. So I have told you that the resolution of this PWM is 16 bit. So maximum value it can go up to 65536. But what we are going to do? We are going to reduce this resolution and you have to limit it to 255. So our results should be observable. Okay. Now after this, here the PWM mode should be one. Keep it as it is. No need to change anything. And the CH polarity should be high. Okay. So actually PWM is very deep concept. So CH pole, CP pole. So there are many concepts. So we are not going to delve in that. We have to just configure this timer and we have to observe the waveforms. So this part is done completely. Now what we have to do? Let's generate the code. So here in the code you can see that we are having the timers. Okay, so this is our timer. Okay, now again the problem of little bit there is with the STM. So it has not been configured for 255. So I am doing this manually. Okay, whenever you generate the code, after that just check it a little bit for any of the issues. Okay, now what we are going to do for using PWM signal, we are going to need this handler. Okay, for PWM this is the handler. So right now what we are going to do, simply we are going to call the handler to start the PWM. Okay, so how to do that? So again HAL, so we are having built-in library HL timer. So for PWM we have to call it PWM. Here we are having option of start. Okay, so by default it is showing HTIM handler, that is timer for handler. So you have to mention here channel. Okay, so you can mention channel 1, channel 2, channel 3, any of the channel. So let's make it as PIM. So we are using in settings, we have set channel 1. Okay, so the timer, here we have to mention the CH channel 1 we are going to use, that is associated with our PA6. Okay, here also we have mentioned the PWM generation CH1. So this one pin associated with timer 3 channel 1. Okay, so this part has been done. Now how to use it? So for using, we can do two things. We can manually write whole code in one chunk, or otherwise what we can do, we can define a function. So let's make a function. Now some of you might have done coding regarding to the Arduino controller. okay, Arduino microcontroller. If you want to generate PWM signal in an Arduino microcontroller, in that case you are going to need one inbuilt function that its name is analog write. So we are going to make our own analog write function over here. So here I am going to write declare a function void. Okay, void means your function is going to return nothing, analog. I'm going to use same case that is used in your Arduino controller. So analog write. So we have to provide the handler here. So handle type definition. Who is the handler? So we have to point towards the handler. So it is H timer. Okay. After this, we have to mention the channel name. We have to pass the channel parameter as well as duty. That is your duty cycle. So here we are going to take u. The channel type will be uint underscore uint 32 underscore t, and variable name will be channel. Okay. After that, uint 8 underscore t, that will be the duty cycle. Why we are taking uint 8? Because the maximum value for our channel cycle is 255. We are limiting it to 255. So here we are mentioning the duty. Now what we have to do? So here what we are going to do, we have to check whatever the incoming duty cycle is below or equal to your 255 value. So here we are writing if duty is greater than 255, okay, or otherwise you can reset the duty is 255. Yes. So after this, what we are going to do, we are going to call our HAL timer. HAL underscore timer. We have to set and compare the values for the timer. So set and compare. Okay. For comparison, we are going to need three parameters which are suggested over here. First one is your handler, second one is channel, and third one is the duty. Okay. So H tim, that is your handler of timer. Here we are using the channel event 32. So we are just passing these parameters. You're taking these parameters and you're passing it over here. And your duty done. Okay. Now what will happen? It will keep the duty cycle below 255. After that, second thing, what will happen? These two things are going to get compared. Okay, I'll explain you that in the waveform directly. Now we have to call this function. So this is our analog write function. We have to call this function. So how to call it? So here we have already turned on the timer. Okay, now here we have to just mention the TIM, and here we have to just mention the PWM. Okay, nothing more than that. Now, how to use this? So let's go inside our while one loop. Here what I am doing, for I am declaring a simple variable. So for you int 16 underscore t. Okay, you can use int also, no problem. So u means it is for unsigned. I is equal to 0. Initially the value of I is 0. I is less than equal to 255. Okay, we are just doing the counting I plus plus. Okay, inside this for loop, what we are going to do? So we are going to call our analog write. Analog write. We are going to pass the timer. We are going to pass the channel. So here channel is TIM underscore channel 1. underscore channel 1, and duty is your duty cycle, that is going to change every time, so that is I in this case. Okay, so I is initially it will be 0. Okay, from 0 it will start, so here the I will be 0, and from here it will come to this point. Okay, so from 0 up to 255 our cycle is going to run. After that it is going to come back over here. Okay, again it is going to increment once, that is 2, so it will run from 2 to 255, like this the cycle will go on. Okay, so we are going to observe this from the waveform itself. Here we are going to introduce a small delay, so we will be able to observe it easily. So delay of, let's put only 20 milliseconds, not going to need much. Now what will happen here, so it is going to grow from 0 to 255. Okay, so let's observe the waveform first to get the clear idea. So let's build this. To get the hex file, right click on your project name, properties, C++ build, settings. Here post build outputs, you have to click on the hex files, both the hex files. Apply and close, rebuild the index, apply and close. Let's build the code again. And here we are going to get the hex file. So let's move to the Proteus first. So in Proteus, let's open the previous diagram, LCD demo. And this only we are going to make the changes. So let's delete the wiring over here. Okay. So now what we are going to do, we have to attach PA6 with the oscilloscope. So here we are having virtual instruments mode. Here we are having oscilloscope, the first option. I'm going to place it over here, rotate 180 degree, and here we are going to connect this yellow line, first channel, channel 1 to PA6. Okay, so here we have to upload the code. So we have designed the new project. So that is PWM demo, debug, and here our hex file is present. Okay, so let's run this first. So you can see that we are getting one waveform. Okay, okay, let me increase the amplitude a little bit. So you can see that the waveform is just increasing. Your turn on time is increasing. Okay, as your value of I is incrementing. Okay, as your value of I is incrementing, the turn on time of your PWM is increasing. You can observe that. Okay, so I'll stop the simulation for a while. Let's jump back to our code. Now what is happening actually? Okay, we are continuously passing value of I over here to this analog write function. Initially, I'm going to write this in the comments. So initially I is 0. What will happen? What will happen? So in case I is 0, so what will happen? The turn on time is 0 in this case. Suppose the I is 50. Okay, so what will happen? The at 0th position, your PWM will start turn on. Okay, and it will remain on until and unless it goes up to 50. Okay, means here your duty is compared with the ARR resistor, auto reload resistor. So our limitation is 255. What will happen? It will start from 0 to 50, it will remain on, and after that up to 255 it will remain off. So this will be your turn on pulses, or you can see it as your turn on steps. Okay, so at 50 it is going to get turned off and it will remain off up to 255. Okay, so this is how it is. Now a little bit about the calculation. So we have kept the clock frequency at 8 megahertz. Okay, so our clock frequency is 8 megahertz. Now we have little bit of calculations to do. Now how those calculations are? So first we have to suppose we have to find out the frequency of the PWM wave. Suppose this is our PWM wave. Okay, this see initially it is when I is 0, so your width of the pulse is very low. Okay, and as I increases, so the turn on time is increasing, and this part is your 255. Okay, this part is your 255th step. Okay, so up till 50 it is turning on, and after that it is turning off until the 255th level. Okay, now what are the calculations we have to take in the account? So if you want to find out the frequency of your PWM signal, the formula is very simple. So formula is your frequency is equal to your clock, CLK clock, divided by prescaler value plus 1. Okay, so our prescaler value, let's check our prescaler value. So this is your PLLCK, that is your prescaler. So we are not providing any value for any prescaler. Here we are having AHV prescaler. The value is 1 over here. Okay, and your frequency is that we are taking is 8 megahertz. So for the calculation, what we are going to do, just a second. So here, let's go to the main code. So here, the prescaler value is, in our case, is 0. Prescaler value is 0. Clock frequency is your 8 megahertz. Clock frequency is your 8 megahertz. Okay, so 8 megahertz divided by 1 will be remaining 8 megahertz. So here your main frequency is 8 megahertz. Now, to find out the PWM frequency, is simple. PWM F is equal to, so your this main frequency F divided by, now this frequency we have calculated is the frequency received by your timer 3. Okay, this is not the main clock frequency of the controller. This is the frequency of the timer circuit that we are using. In case if your prescaler changes, see the frequency is getting reduced. Okay, so we have kept it as 1, so it is getting the maximum frequency for the timer. Okay, so you have to keep this in mind. Okay, now your main frequency divided by divided by ARR plus 1, that is auto reload resistor. Okay, that is your auto reload resistor. So where is our auto reload resistor? So here is our auto reload resistor. So we have tried to configure it 255, but it's not working that way. So in main code, what we have done, in main code we have configured it as 255 over here. Okay, so 255 plus 1, that is your 256. Okay, that is 255 plus 1, so it will become F divided by 256, that is 8 megahertz, that is 8,000,000 divided by 256, that will be equal to 31250. Okay, so roughly you can say it as 31 kilohertz KHZ. Okay, now why I have kept the frequency so low, so we'll be able to see the flickering of light visibly. Okay, we should be able to observe the output carefully. For that we have kept the frequency low. Okay, otherwise we can increase the frequency up to 72 megahertz also, no problem. We can use these prescalers and you can multiply the frequency up to 72 megahertz. Okay, so let's jump back to the code. Okay, now I'll remove the delay. Okay, so here I'm going to keep it only 1 millisecond, and let's recompile this. I don't want to generate the code. So we have compiled it. Let's jump to the Proteus. Let's play the simulation. Okay, now you can see that the PWM on time is increasing very fast. Okay, so it is just increasing and suddenly it is going to get diminished. Okay, so let's upload this on hardware. Okay, and we'll see what output we can get and how to observe that output. Okay, so we're going to see that in next session.